Hey all, sorry I missed you week 2. In order to keep up a nice momentum for this course, I'm providing your lecture via video, and I'm going to be discussing some concepts with you and then have you do some work outside of class, just as you would have done inside the classroom to learn more about this concept of GD&T, which is known as geometric dimensioning and tolerancing. So first things first, let's talk about the term tolerance. If you remember from your CAD classes or other classes, tolerance is an important term because it tells us a little bit about what's good enough, or in essence, the allowable variation in a part size, depending on what the part must ultimately function or what its purpose is, will depend on what limits will be set for variation. Well, one thing we're going to do is use measurement to determine whether part sizes fall within or outside of tolerance. Parts that fall outside of tolerance will not meet the customer's specifications and ultimately will not function to their desired intent. So geometric dimensioning and tolerancing is really interesting because it takes our standard tolerancing that we're pretty used to, which is traditional tolerancing methods, and allows us to do a lot more with that by looking at specific types of tolerance zones and focusing on basically features that are critical to a part's functionality. So to define that a little bit better, you'll notice that geometric dimensioning and tolerancing, which I will now refer to as GD&T for the rest of this class, is a universal language that's designed to basically convey the designer's intent, what the designer is looking to do, all the way from design to fabrication of that part to expecting the parts to see if they did fall within the desired intent. The beauty of GD&T is that it controls form and fit, and form and fit is an important concept to think about because without proper form and fit, systems can't function properly. So this really does lead to better functionality of parts. When should geometric dimensioning and tolerancing be used? Well, there's a few things to think about when it comes to using GD&T. First off, if we have features that are critical to functionality, and especially a good example of this would be interchangeable parts, GD&T is going to work out really well. If datums are required, and we'll talk about datums a little bit more in just a moment, GD&T is another useful resource in doing this properly. And of course, when tolerances are not implied, if tolerances are going to change throughout a part's different features, and the implication isn't enough on a detailed drawing, it's important that we call out these tolerances using GD&T. So the benefits of using GD&T. I'm going to visually show you what a benefit is in just a moment, but one of the biggest benefits is that it adds clarity. As engineers, we are really here to be communicators, and in doing so, we have to do this as effectively as possible. GD&T is a universal language used globally to describe how we intend to build something, and this allows us to basically open up the communication gaps and really be able to move forward from design intent to completion of the production. So one of the biggest benefits of GD&T is the allowance for larger tolerance zones, which I'll show you in just a second. And because we widen up our tolerance zones, parts that traditionally might be considered to fail upon traditional analysis may actually be passing parts and allow us to have less scrap and rework in what we do. So if you want to learn more about the governing standards regarding geometric dimensioning and tolerancing, ASME is our standard organization for this. And the standard that's used is Y14.5M, dimensioning and tolerancing. That tells you how we actually apply these GD&T symbols properly in order to use them to their fullest potential. So here's a little example of why GD&T is so effective. If you notice here, we're looking at just the center of a circle. And let's say that this is the center of a hole. And we need that center of the hole to fall within a certain framework, because if the center is outside, then we know the circle is going to be offset, and either it's going to be a pin that doesn't fit into a hole or a hole that won't be able to be used properly for another pin. So traditionally, tolerance zones look like this. They may be square or rectangular. Notice that we are speccing out the center of the circle by adding or subtracting, let's say, 5/1000 of an inch top and bottom, and adding and subtracting 5/1000ths of an inch left and right. Notice the zone that we get in doing so. The center of this drill can fall within this rectangular zone. You probably heard the irony in that statement already. Drills, when they spin, create circles. They do not create squares or rectangles. So why are we using a geometric feature to call out a tolerance zone that it doesn't really fit the practicality of the piece we're using to make that feature in the first place? What geometric dimensioning and tolerancing does is use what's known as diametrical or circular tolerance zones so that that center of the drill can fall within this circle. And if you notice, this square could actually be inscribed in this circle. The diagonal of this square is equal to the diameter of this circle. What that means for us is an additional area of about 57% of the original area that you see here, which means that in some cases where our center of our drill may be just outside these boundaries, falling out of spec in this situation, by using geometric dimensioning and tolerancing, that center may actually fall within this circular boundary. And for that reason, that will allow us to actually see that that part will function regardless. So this is a critical aspect beyond just better communication and being able to relay design intent more effectively. This also allows us to scrap less parts, ultimately leading to more potential gain. So here are our 5 different types of geometric dimensioning and tolerancing standards, and please know these. GD&T is designed to really help us better understand form, profile, orientation, location, and runout. And you'll notice that these are the different characteristics that fall in each category. Here's a perfect example. If we think about orientation, how a part is supposed to be oriented. Angularity is an important orientation. If we need let's say the face of a part to fall within a 45-degree difference between the base of the part, we'd have to be able to measure that. And we can use this angularity feature to actually help us do that a little bit better, to say what that angularity should be within a certain amount of degrees. And we'll look at these in greater detail. In fact, you're going to be doing some work to look at these in greater detail very shortly. Another example might be something like flatness. Notice that flatness is a feature of form. In fact, flatness is interesting because it's very unnatural. Try to find something on Earth that's purely flat. Tough to do. Well, if we take a look at the symbol, if this flatness characteristic is applied to, let's say, a plane, then that plane has to stay flat within a certain amount of, let's say, thousandths of an inch or hundredths of a millimeter, so on and so forth. Notice that it does not require a datum because features of form never really require a datum. They don't need it. When it comes to something, if we go back to angularity, angularity always needs a datum because we need to define a plane or a line that we're going to base that 45-degree angle off of. So in working with geometric dimensioning and tolerancing, we spec this out on a detailed drawing using what's known as feature control frames. And here you can see an example of your feature control frame right here. Notice that this is the geometric dimensioning and tolerancing callout. Now, something to know about your feature control frame. This doesn't tell you anything about the size of the hole. In fact, this is a position tolerance. This is simply telling us where that hole should be located. In fact, where the center of that hole should be located. Traditional tolerances, like the size limits on the diameter of the hole, will actually be found above the feature control frame. This is dedicated to solely GD&T. Now, what this says here is that the position must fall within a diametrical tolerance zone of, let's say, 0.2. Let's say we were working in millimeters, which means the center of that circle can fall anywhere within a 0.2 millimeter diameter circle from the original location of that center. This M we'll talk about in just a moment, but this means maximum material condition. So this standard would be true at maximum material condition. Now, if this was a hole, and the hole was actually not at maximum material condition, which means the hole would be a little bit larger, we may have a little bit more wiggle room as to where the location of that center of the hole will be. So another important aspect of GD&T will be maximum and least material condition. And you'll be reading a little bit about that in the unit I ask you to read to be prepared for this lecture as well as next class. So these three boxes right here represent our datum planes. Notice the most important datum, our primary datum goes first, our secondary, and then ultimately our tertiary datum. These could be three datum planes that we used to basically orient the part and understand where its X, Y, and Z axes will be. We'll talk more about that shortly as well. And we're going to do a lot of work with this stuff in Pisademus, our software that runs the CMM. Notice that features of form, like flatness, do not require a datum, so you're not going to see a datum listed here. Here's an example of a detailed drawing. And you can see there's a lot going on here. And our limitations in analyzing this drawing are really more so regarding what are we trying to produce and how are we trying to produce it. But I want to give you guys a sense of what a detailed drawing looks like with these feature control frames listed. Notice in this example, it appears as though the center of this hole needs to be perpendicular to both datums A and B within a tolerance zone of, in this case, let's say 0.003 of an inch. So take a moment and look through these, and you can break this down further in your textbook as well. But these feature control frames are very, very important to us in order to relay what features we're trying to control. Notice in this case, we're looking for axes to be parallel. In this case, we're looking for axes to be perpendicular. And we can also be looking for perpendicularity and parallelism with axes, let's say the center of a bored out hole, or planes themselves. Let's say that this top plane needs to be perpendicular to this bottom plane, which if you notice has been named as datum A. So that parallelism must be there in order for this part to function properly. So we're going to be working a lot with geometric dimensioning and tolerancing when we start to get into Pisademus, our software that runs our CMM. Pisademus is a great tool that allows us to build manual or automated measurement programs. So we may build a program that an operator will repeat manually on the roamer arm, which we'll get some time to work with, or maybe we'll build a program that will be able to be automated. So another operator can position the part, align the part, and then run the measurement program without having to manually take the measurements. Instead, the machine will do it, such as our SF454, our automated CMM that you'll be working with as well. If you notice this red leader line right here, these are all of our geometric dimensioning and tolerancing symbols. So once we've, let's say, for instance, we import a CAD model, we'll be doing this shortly, and we start taking some measurements off the CAD model by measuring some features. Then once we've measured our features, what we'll do is actually assign tolerances and geometric dimensioning and tolerancing constraints using these tools. If you've got a lot of questions there, good, because we've just tipped the iceberg here. I'm going to be teaching you a lot about Pisademus. So let's go back to a concept that's a critical concept when it's related to geometric dimensioning and tolerancing, and a pretty critical concept regardless, and that's the datum. Your datum is basically your standard or your means for comparison. A datum is a theoretically exact plane, point, or axis from which a dimension is measured. In essence, basically, it's a reference point, plane, or line. Look at this example right here. Notice that you often in SolidWorks have to determine whether you're working with the front plane, the bottom plane, the left plane, the top plane, so on and so forth. And you begin drawing from that plane. You can look at that plane as your datum. Everything's based off of that plane. And let's say that the origin of this part, we can't see it, but is in this bottom right corner. Notice that these three datums, when pushed together, create a datum reference frame. And the intersection point of all those datums would really be the origin of this part. So datums can be planes, datums can also be axes. Let's say that everything we do is based off of this hole here. We want to know that this slot is a certain degree, or let's say a certain length away from this hole, and that the center of this hole is in line with this guy. We may use the center of this hole as our datum and reference all of our tolerances off of that datum.